Okay, geometry, now that we've knocked out everything we needed to learn about the Pythagorean theorem from section 8.1, we're going to move on into section 8.2. And this is really the second of three big ideas that we're going to talk about here in chapter 8. This one is called special right triangles. Kind of a weird title for it, I understand that, but hopefully we'll get the hang of this one pretty quickly. What you guys are going to need to do right now, everybody, is to make absolutely certain that you've got a piece of paper, I don't know, maybe your notebook, and then a writing utensil, a pen or a pencil next to you. Because in every single year, I say the same thing, and this year it's slightly different, but the idea is still true. You have absolutely got to have a couple of ideas normally memorized. This year we're just going to say written down and in a place where you can access them quickly, because these are patterns that occur in every one of these special right triangles, and it's going to be difficult for you guys just to watch this video and say, oh, okay, I get it, unless you're writing it down and then practicing these ideas on your own. So the good news here is, everybody, there are only two special right triangles that we need to learn about. And the first one here is called a 45-45-90 right triangle. So I have it drawn over here on the right-hand side, and as you've probably figured out already, the numbers 45, 45, and 90 represent the measures in degrees of the three angles of this triangle here. Two of our acute angles are both 45 degrees, and then we've got a right triangle here because it has a 90-degree angle as well. So 45, 45, and 90. Now, let's go back to a property that we learned in chapter 4 that said that if a triangle has two congruent angles, and this one does, the 45-degree angles obviously are congruent to each other, then the sides opposite from those congruent angles, such as the bottom leg and the left leg, they have to be congruent to each other as well. So a triangle with two congruent angles must also have two congruent sides, and that is the definition of an isosceles triangle. And as I said earlier, the fact that it has a 90-degree angle makes it a right triangle. So a 45-45-90 triangle is the one and only isosceles right triangle. It's the only triangle you could ever draw that is both isosceles and has a right angle in it. So that is what a 45-45-90 triangle looks like. And what you guys absolutely need to have either memorized in most years or written down this year are the lengths of the three sides in a 45-45-90. One of the legs we're going to generically call x, meaning that that can represent any positive number. Obviously, the length of a side in a triangle can't be 0 and it can't be negative, but any positive number you could think of, x can equal that. The other leg, as you may have figured out already, is going to be x as well. Why? Well, because of the reason we just discussed. If this triangle has two congruent angles, the two at 45 degrees, it must also have two congruent sides. So however long your first leg is, your second leg needs to be congruent to it. And the hypotenuse in a 45-45-90 triangle is always going to be x multiplied by the square root of 2. And I'd like to explain that for just a second. You don't need to write down anything that I'm going to do here in green, everybody, but if we didn't know that that piece was x root 2, and we just said, okay, here's my hypotenuse. I didn't want to do that. All right, and I said, all right, here's my hypotenuse, and I'm just going to call it h generically for the length of the hypotenuse. Let's see if we can't draw a connection between x, the length of our legs, and h. Well, what do we know, guys? We know that because this is a right triangle, the Pythagorean theorem applies. Leg squared plus leg squared equals hypotenuse squared. So there's step 1. Step 2, fill in what you know. How long is one of our legs? X. And don't forget to square it. How long is your other leg? Also x, and we'll square that. And how long is our hypotenuse? Well, right now we don't know, so we're going to call it h. And there's actually very little that we can do from here other than noticing that we have two like terms here on the left-hand side being added together, both of which have a coefficient of 1. And when you're adding like terms, guys, like, I don't know, 3n plus 5n, everybody knows how to do it when I put it in this context, right? Those are like terms, so we add the coefficients, 3 and 5 make an 8, and then we keep the common factor, n, exactly the same, and there's a statement that just about everybody at this level feels comfortable with. 3n plus 5n is equal to 8n. Well, if we do the exact same things, everybody, up here, we have two like terms here, so we add their coefficients. 1 plus 1 makes a 2, and then their common factor of x squared stays exactly the same, and that left side just becomes 2x squared. Now, what we're really trying to do here, guys, is figure out how long the hypotenuse is represented in terms of x. So we really want to solve this equation now for h. So h is on the right, it's being squared, and the way we undo a square is with a square root on both sides. Now on the right, the square and the square root cancel, and I'll switch sides here, guys. That just leaves us an h. And now, to simplify the square root of 2x squared, we're going to use a property that this year we kind of glossed over in section 8.1. But that property says that the square root of a two-factor expression, 2 times x squared, can be split up into the square root of 2 multiplied by the square root of x squared. That is how we simplify radicals, everybody. That's how the square root of 20 becomes 2 root 5, for those of you who have the fancier calculator. For now, this year, I know we skipped that, and I'm going to ask you guys to trust me on that one. Now, the square root of 2 is an ugly, irrational number. It's 1.414, blah, blah, blah. That's as much as I have memorized, but we're not going to do that. We're going to leave it as the square root of 2. However, I hope you notice this, the square root of x squared can be simplified. The square and the square root cancel each other out. So we end up then with h is equal to, the square root of x squared is x. I'm going to move that in front, and you can't do anything with the square root of 2. So that's the best we can do, guys. The hypotenuse of a 45, 45, 90 triangle whose legs have a length of x, its hypotenuse has a length of x times the square root of 2. So I'm going to get rid of all this green junk here. All right, and let's go back to where we were a second ago there. And all right, I've already got that boxed up in red. So if your leg has a length of x, your hypotenuse is going to have a length of x multiplied by the square root of 2. Let's see that in action now, everybody. That's really about as much theoretical stuff as we need to know today, and let's see what's going on here. I've got 2 examples on one slide. That ought to tell you these aren't going to take very long. Once you guys get that pattern, what's inside that box in the top right here, once you get that down, these problems go incredibly quickly, and very often there's no work at all to show. And in the worst case scenarios, there's a little bit of work, but not very much. So let's see what's going on here in A. First question, we never want to assume, is this a 45, 45, 90? Well, yeah, this one pretty clearly. I see 2 angles of 45 and 45 and a right angle there. So yeah, that one's a slam dunk. It's a 45, 45, 90. One of our legs is given to us with a length of 8. We need to come up with the length of the other leg and the length of the hypotenuse. So let's get started. How long is the other leg? Well, because this triangle is isosceles, the 2 legs are congruent to each other, so x has to be congruent to the other leg. X is going to have a length of 8. And then for y, this one's just a little bit harder. If we go back to the diagram here, to go from a leg to your hypotenuse, whatever x is, you're going to multiply that by the square root of 2. So in this example, since our legs are 8, our hypotenuse is going to be that leg, 8, multiplied by the square root of 2. And usually we don't put the dot there, guys. We just write that as 8 root 2. And I got to, that was ugly. Let's try that again. So 8 root 2, that's much better. And guys, I have good news for you. We're done. That's the answer to that problem there. X is equal to 8 and Y is equal to 8 root 2. Now, you guys know me, I can't just leave it at that. Let's remember something that we talked about in the last section in 8.1. If you're done with a problem involving a right triangle and you want to make sure that it's right, one thing you guys can always do is this little trick that I taught you. Hypotenuse squared minus leg squared should always equal the magic number of 0. The one thing you're going to have to be careful about when doing it is if you're going to put this hypotenuse, 8 root 2, in your calculator and square it, you're going to have to put parentheses around the 8 root 2 so that both the 8 and the root 2 get squared. Now, everybody, I have got my fancy pants calculator loaded up. Let me get rid of that. Let me do one a little bit more like what you guys might be using. I'm a big fan of this Desmos scientific calculator here, and you guys are going to be using the Desmos graphing calculator a lot next year in Algebra 2, so might be worth practicing. Okay, I'm going to hit my parenthesis here and type in 8 times the square root of 2. Closed, no, that's not what I wanted. I needed to hit a right arrow to get out of there, just like on a TI calculator. Okay, so there we go. There's our hypotenuse, and we're going to square that. Minus, one of my legs is 8 squared, and minus the other leg of 8 squared, and this should equal 0. And what I ended up with, dang it, I hate it when this happens, 2.842 blah blah blah, but times 10 to the negative 14th power. For those of you that don't remember scientific notation really well from last year, because of that negative exponent, this is an incredibly small number. In fact, what this number is written in standard form is 0. And then I believe, if I remember this right, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros, and then a 2, 8, 4, 2, and so on and so forth. Guys, that number is really, really, really close to 0, and it should be exactly 0. And frankly, if I was using a better calculator, it would be, but that's as much as this calculator is able to handle. Let me show you, let me go to my fancier calculator. I don't want you guys thinking that I'm lying to you here. This calculator should handle this correctly. 8 times the square root of 2, get out of there, close the parenthesis, and square it. Minus 8 squared minus another 8 squared, and I believe the TI Inspire CAS won't let me down. That gives me the exact answer of 0 that I was looking for. This is an incredibly sophisticated calculator that I'm using right here, guys. So anyway, back to it. This little test here worked out, so I feel pretty good about that answer. All right, let's move on to B. Now, B is really the same problem as A. Let's talk about why. First things first, is it a 45, 45, 90? Let's not assume. Well, all I see for a fact right now is that it has a 90-degree angle right here, but I don't see the 45s the way that I did back in example A. But what I do see are tick marks here and here. This triangle is isosceles. And a triangle that's isosceles has 2 congruent sides, but that also means, because of a theorem we learned in Chapter 4, that it must also have 2 congruent angles. So these 2 angles here, plus the 90-degree angle, have to add up to 180. And since these 2 angles are congruent, I would take 180 minus the 90 that I know right here and get 90 left over for the 2 to share, divided equally by 2. Yeah, they both need to be 45. Okay, but long story short, guys, let me go back to before I started messing up this whole diagram. What kind of triangle were we given? We can tell right away from it that it's a right triangle because of the corner mark and that it's isosceles because of the tick marks. And as we said back here, the only right isosceles triangle is a 45, 45, 90. Okay, so let's get started. We've been given the length of one of our legs, which is ugly now. It's irrational. It's 11 times the square root of 2. D then. That's not what I wanted to have happen. Let's try, that's weird. Why are you doing that? Okay, D is equal to, is that D still showing up here? Very odd. And now it disappeared here as well. That's creepy. It's haunted. All right, D is one of my legs, which is congruent to this leg right here. D is also going to be 11 times the square root of 2. E, though, is just a little bit more interesting. E is the hypotenuse. And if you look back at example A, the way we got from leg to hypotenuse was to multiply your leg by the square root of 2. And in A, we simply took 8 times the square root of 2, and you can't simplify that at all. We got 8 root 2. But here in example B, you take your leg, which is 11 root 2, and we multiply that by the square root of 2. And I would really, really like it if you guys did not need to go to your calculator in order to figure this out. Now, this is something, again, that we've kind of brushed over this year, but I think I can explain it to you guys pretty quickly. What we're doing right here is multiplying the square root of 2 times the square root of 2. So that is 11 multiplied now by the square root of 2 squared. Okay, any number times itself is that number squared. And now I'm hoping you see that the square and the square root on the 2 cancel each other out. So we end up with 11 multiplied by 2, which of course is going to equal 22 for the value of e. All right, so our hypotenuse is 22. We'll put that right here. And both legs had a length of 11 root 2. So what do I want you guys to take from these two examples side by side? In example A, both of the legs were whole numbers, were 8, and then the hypotenuse was irrational with a root 2, 8 root 2. And in B, both of the legs were irrational, 11 root 2, and that gave us a rational hypotenuse of 22. So it's kind of got to work one way or the other. It is possible for them all to be irrational. If I threw in like a weird number like square root of 7 in there, there's no getting around that. But it's impossible for them all to be rational numbers. All right, let's do 2 more examples with this, just to see how the plot can thicken a little bit. Okay, what's going on in C? For starters, don't just assume. Is this a 45, 45, 90 triangle? Well, we see the 45 and the 45, but we don't see a 90. It certainly looks like there's a right angle right here, but let's think about how we might know that. One of the most fundamental, basic, and universally important things that you guys need to know coming out of geometry, and it should stay with you for a while, is that the sum of the measures of all 3 angles in any triangle always has to equal 180. So if you know 2 angles, you can always do a quick little bit of math and find the third. 45 and 45 add up to 90, and 180 minus 90, of course, leaves us 90 degrees for the third angle. So it wasn't given to us, but we were able to figure that out. Now, what makes this problem very different than the last 2 is that in both examples A and B, we were given a leg and we had to figure out the hypotenuse. How? By multiplying the leg times the square root of 2 to get from leg to hypotenuse. But now in problem number 3, or excuse me, example C, we've been given the hypotenuse, everybody, and we now need to go backwards in order to figure out the length of our legs here. So how are we going to do that? Well, by simply reversing the process that we came up with before. G is a leg, everybody. And what have we learned? To go from leg to hypotenuse, you multiply by the square root of 2. So to go from hypotenuse back to leg, we're going to reverse that and take our hypotenuse, 17 root 2, dang gummit, that's not what I wanted. That's even less what I wanted. 17 times the square root of 2 is your hypotenuse, and now we need to divide that by the square root of 2. And once again, everybody, you do not need a calculator here. What I'm hoping you see is that there are identical factors of the square root of 2 on both the top and the bottom of this expression that simply cancel each other out, and G is this nice rational number here of 17. Now, how about H? Well, I'm hoping you get the joke here already. This is an isosceles right triangle. Your 2 legs, G and H, have to be congruent to each other. So whatever you got for G, H is going to have to be the exact same number of 17. So we have a right triangle here with legs of 17, 17, and a hypotenuse of 17 root 2. Really no different than what we did here in example A, where we ended up with legs of 8 and 8 and a hypotenuse of 8 root 2. Okay? So not too bad of a problem. So what have we learned? To go from leg to hypotenuse in a 45, 45, 90, we multiply by the square root of 2. To go backwards from hypotenuse to leg, you're going to divide by the square root of 2. And D is really kind of the same thing, although with a little twist. But again, almost the most important thing we're learning here with these problems, how to figure out what kind of triangle we are dealing with. And all I see right now is one angle, not even two. I know there's a 45, so it could be a 45, 45, 90, but do we know for a fact that it is? And it doesn't look like it at first, but let's dig a little bit deeper. They gave us tick marks. There are two sides in this triangle that are congruent, the one labeled J in the top left position and the one labeled K in the top right position. So since this triangle has two congruent sides, that makes it isosceles. And a triangle with two congruent sides must also have two congruent angles. So this angle here has to be 45 degrees as well, even though they didn't tell us that. And now that we know this triangle has two angles of 45 and 45, then it becomes just like the last problem. 45 plus 45 is 90, and 180 minus that 90 leaves us with a 90-degree angle up here on top. So yes, this is a 45, 45, 90. And once again, just like example C, we've been given the length of the hypotenuse, and we now need to come up with the length of the two legs. So like we just accomplished here in part C, to go from hypotenuse back to a leg, we need to make it smaller. We do that with division. So here, our hypotenuse has a length of 30, and then we're going to divide that by the square root of 2. Now, I told you guys this year, we didn't have to be really worried about coming up with goofy rational decimals, and I said we were going to do most of this in our calculator. So I'm going to try to be consistent with you guys, and I'm going to go back to that Desmos calculator and just type all of this, and I don't want this junk. Clear that out. Okay, so here we go, guys. It was 30 divided by the square root of 2, and that is going to give us a length of 21 point, I usually go two places, so we'll say 21.21. That's kind of poetic right there. 21.21. And of course, K, being our other leg, is going to end up being the exact same length of 21.21. All right, so there are our answers to problem D. Okay, nothing too shabby, everybody. All right. Those are the 4 examples I wanted to do with you guys that all dealt with the first type of special right triangle that was the 45, 45, 90. Now we're going to shift gears completely and move on to the second big type here, and that's going to be called a 30, 60, 90 right triangle. And once again, as you've probably gathered already, the 30, 60, 90 refers to the degree measures of your 3 angles. We've got a 30-degree angle here, kind of the skinniest, sharpest of the 3 angles, a 60-degree angle, which is a wider acute angle, and then a right angle right here in the bottom left corner in this case. And here's what we need to memorize now, everybody, that the 3 side lengths in a 30, 60, 90 triangle are x multiplied by the square root of 3, and 2x. And we're going to be just a little bit more specific right here. This piece that we have labeled x, that one we're not just going to call a leg, we're going to call that the short leg. And if you remember from something we learned back quickly in chapter 5, the shortest side of a triangle is always opposite from its smallest angle. And that 30-degree angle is clearly the smallest of the 3. That means that its opposite side, x, is the shortest side. So x is what we call the short leg. X times the square root of 3 then is what we are going to call the long leg, and the 2x over here is the hypotenuse. And let's not forget, guys, the hypotenuse must always be the longest side. So that can be a little bit confusing right here because your long leg is the longer of the 2 legs, but it's the middle out of the 3 sides. Okay, so the pattern we need to have memorized here in a 30, 60, 90 is x root 3, and 2x. I never really wrote that out that way for 45, 45, 90s. But that one, in fact, let me go back and do that here. Did I leave myself any room? It would be x, and then x times the square root of 2. So that's the pattern you're going to need to have memorized, or written down, as it were, this year. With a 45, 45, 90, here's what it is on a 30, 60, 90. Okay, again, I'm going to walk through this in green. You guys do not need to write down or really even pay attention to much of what I'm going to do right now. I just find this interesting. I don't know if some of you might. The way this pattern developed is it actually starts, everybody, with a triangle that we know a little bit about. We're going to start with an equilateral triangle. And to show that this is equilateral, I'm going to put a double tick mark here and a double tick mark here and a double tick mark here. Now, the fact that this triangle is equilateral guarantees that this is a 60, 60, 60 triangle. Every equilateral triangle with 3 congruent sides must also have 3 congruent angles, and 180 divided by 3 is 60. But what we're going to do right now, you guys, is we're going to draw a line segment here that bisects this angle up at the top and also bisects the bottom side of this triangle. Now, that piece right there is going to be perpendicular to the bottom side. And this 60-degree angle up on top just got cut into 2 congruent pieces. So that is where the 30-degree angle there comes from. And if you haven't figured out where I'm going with this yet, take a look at what I'm highlighting in yellow. That, everybody, is a triangle with one right angle in the bottom left corner, a 60-degree angle in the bottom right corner, and a 30-degree angle up on top. That is where this triangle up here comes from. Now, let's talk about side lengths. I said that the original big triangle was isosceles, so I'm going to say that this side over here has a length of 2x. You'll see why I did a 2 there in just a second. The important thing, though, is that all 3 sides in that triangle are congruent, so this one is 2x as well, and the entire bottom side was 2x also. But what happened? We drew this bisector going right down the bottom here, guys, so when it hit the bottom right here, it cut the bottom side of that triangle in half. So that piece that I just highlighted in red is just x. So that explains, everybody, right here where the 2x comes from. This bottom side is half of the base of that equilateral triangle, so that's where the x comes from. And yet again, we don't know this yet, but let's see. That altitude that I drew right down the middle, I'm going to call that h. And yet again, I'm going to set up a Pythagorean relationship here within that triangle. Leg squared plus leg squared is equal to hypotenuse squared. Okay, how long is one of our legs? H, and we'll square that. How long is the other leg? X, and we'll square that. And how long is the hypotenuse? That is a 2x. And you got to be careful here with the same reason I talked about earlier. We've got to put parentheses around the 2x before we square it. And just like we did before, we're trying to solve this thing for h. Now, there's not anything that we can do right now to clean up the left side. H squared plus x squared equals. But on the right, guys, 2x quantity squared means, let me write this over here, 2x multiplied by itself, 2x. And what people forget here all the time, when you're multiplying monomials, you multiply their coefficients. 2 times 2 is 4, and x times x is x squared. Without the parentheses there, people usually just write 2x squared here instead of 4x squared, and I got bad news for you, that is wrong. Now what we're going to do next is try to get h by itself. So we're going to subtract a 1x squared from both sides. Those terms cancel, and we're going to get h squared is equal to, and a 4x squared minus a 1x squared is going to get us a 3x squared. And to solve for h, we'll take the square root of the left and the square root of the right. The square and the square root cancel, so we're going to get h is equal to, and let's see, I think I finally learned how to give myself a little more room here. Let me bring that down a little bit. Okay, we're going to get h is equal to, now the square root of 3x squared, we're going to break that up the same way we did back in the first slide. This is the square root of 3 multiplied by the square root of x squared. And you can't do anything with the square root of 3, you guys. It is what it is, but the square root of x squared becomes just x. So h is x multiplied by the square root of 3. And that, everybody, is where this comes from. That was the length of this other leg of the right triangle, h, which simplifies now to x multiplied by the square root of 3. So that explains, in a way you guys are never going to be tested on, so relax about that, but that's where this pattern comes from. So it's not just made up, it's not just random, and it wasn't just observed and somebody said, yeah, this seems to be it. This was actually proven here, and we just walked through how to do it relatively quickly. So let's see it in action, everybody. Our first example is going to look like this right here. So we have ourselves a triangle, but once again, let's not make any assumptions about what it is. So let's analyze. I see two angles here of 30 and 60, no 90. But as we said earlier, if you know two angles in a triangle, you can always find the third. 30 plus 60 makes 90, and 180 minus 90 is going to get us a 90-degree angle here. So we weren't given that it was a 30, 60, 90, but we were able to deduce that beyond any doubt. And now let's see where we are. The one side we were given here, the 11, is opposite from the 30-degree angle right there, so 11 is the short leg of your 30, 60, 90. And guys, without question, this is the best case scenario. The short leg is always the one that we want to know first because everything else is built off of that. So let's go back to this diagram because I doubt we have it memorized yet. But if your short leg is x, your long leg is that same number, x, multiplied by the square root of 3. So if our short leg is 11, our long leg, f, is going to be 11 multiplied by the square root of 3. And guys, this is going to be just a beautiful thing for you to hear. There is nothing we can do to simplify that expression. If you want to go to your calculator and figure it out as a decimal, good for you. You can, and I'll give you full credit for it, but I'm not going to do that. 11 root 3 is easier to come up with, and it's also more precise. Now, we need g. And g, in case we couldn't tell, is our hypotenuse. So, back to this diagram. To go from short leg to hypotenuse, we simply take the short leg, which is x, and multiply it by 2. Whoa, shoot. I just did something I don't think I wanted to do. Uh-oh. How do I undo that? I don't think that's going to do it. So let's see. Can I get back into this file? I don't know. Maybe. Saving. Stand by, everybody. We're having technical difficulties. Wow, we're having serious technical difficulties. Sorry about this, guys. Okay. Any day now. I'm hoping it'll be done saving and I can get back into this 8.2 file. And if not, we'll have to just start it fresh. But hopefully the video is still rolling. Wow. This is weird. Okay. Good times. We'll give it another second, and if not, I'll just shut down this app and then open it back up. Okay, good stuff. All right, so let me see if I do this and then head back to it. Nope, same problem. So let's try just shutting that app down and then seeing if we can open it back up and seeing what happens now. Okay, and here we are into the 8.2 file. Okay, and here's where we were, and it looks like we didn't lose anything, so that's good. So back to this. I'm sorry, guys. So where were we? G is our hypotenuse, and to get our hypotenuse, we take our short leg, which was 11. Oh, that's not what I wanted. I did lose my pens. Well, I can fix that. All right. So to get our hypotenuse, we take our short leg, which was 11, and we simply multiply that by 2, and last I checked, 11 times 2 is going to get us 22 for the length of our hypotenuse. Now again, because this is our first example right here, I want to go ahead and test this idea yet again. Hypotenuse squared minus leg squared should equal 0. Let's check it, guys. Our hypotenuse, G, is 22. So let me go... I got burned on this on the Desmos before, but let's try it now. All right. So my hypotenuse was 22 squared minus one of my legs, the shorter one, was 11 squared, and then minus, now here I need parentheses, the other leg was 11 times the square root of 3. I got to hit my right arrow to get out of that radical. I've got to close the parenthesis, and then I need to square that. And this time, it gave me the exact answer I was looking for of 0. Limitations of cheaper calculators, everybody. That one worked out. Okay, so that's example A. And let's be clear, this is the type of problem, this is what it looks like when the short leg was given to you. The next two examples are harder. The second one here, let's take a look at B, all right? And what I think you can see right here, 34 is across from the right angle, everybody. So this side right over here is the hypotenuse. This is what we do when the hypotenuse is given. But before I get ahead of myself, are we sure that this is a 30, 60, 90? Well, I see a 60 right here and a right angle right here. 60 plus 90 is 150, and 180 minus 150 means that other angle must be 30 degrees. So yes, this is a 30, 60, 90. Now everybody, in a problem like this, when the short leg is not given to you, this is the side, the short leg, that you must find first. Hey, I don't know if anybody noticed this. Bears fans out there, take a look at what's going on. W and P, and the side I gave you was 34. Walter Payton, number 34 for the Bears. Anyway, we need to find this short leg first, guys. So let's set about finding W, then we'll worry about P later on. So what did we learn here, guys? To go from short leg to hypotenuse, we multiply by 2. Nice and simple. We double it. To go backwards now, from hypotenuse back to short leg, we are simply going to divide by 2. So W is going to be 34 divided by 2, which is going to give us a nice rational number of 17. So now we know how long our short leg is. P, everybody, is our long leg. And to go from short leg to long leg here, we are always going to multiply the short leg by the square root of 3. So the short leg was 17, and we're going to multiply that by the square root of 3. And here's more music to your ears, everybody, like watching Walter Payton run. It's just a beautiful thing. There's nothing else for you to do on your own right here. Okay, there's nothing to do to simplify this. 17 root 3 is as good as it's going to get. Getting it to a decimal would just make things uglier, so we're going to quit right there. So that really wasn't very much work. If they give you the hypotenuse, you divide by 2 to come up with your short leg, and then you take your short leg and multiply it by the square root of 3 to get your long leg. Done and done. And the last example I have to do with you guys is this one right here. And this is the hardest out of the 3 in the 30, 60, 90 cases, but even then isn't too bad. First things first, what kind of triangle were we given? We see the 90 here and the 30, but not a 60, but let's figure it out. 90 plus 30 is 120, and 180 minus 120 is going to get us 60 degrees. So there's no choice in the matter, guys. This is a 30, 60, 90, even though we had to dig just a little bit in order to figure that out. And let's ask ourselves the question, out of the 3 sides in a 30, 60, 90, short leg, long leg, and hypotenuse, which of the 3 were we given? Well, the 27 that we have here, you guys, is across from the 60-degree angle. 60 is the middle angle, which makes 27 the middle length of the 3 sides. So it's not the short leg, which is the shortest side. It's not the hypotenuse, which is the longest side. This one right here is the long leg in our 30, 60, 90. Now, once again, if you don't already know the short leg, which is J, that's what you need to find first. There's no good way to go from long leg directly to the hypotenuse. We're going to go from long leg to short leg first, and then from short leg to hypotenuse. So we're going to try to figure out J. Dang gummit, I broke it again. Wow. Whew. Having a rough day hitting buttons with my big fat hands here, everybody. Oh, no, I did lose that. Weird. So, oh, man. Mr. Fontana is on the struggle bus here today. All right, so there's that. So we said we were going here, and then we were going here. So to find J, everybody, which is our short leg, let's go back here. Now, to go from short leg to long leg, we multiply by the square root of 3. Then to go backwards from long leg to short leg, we are going to divide by the square root of 3. So j is the long leg, which is 27, and we're going to divide that by the square root of 3. And in this case here, guys, I'm going to say we're going to go ahead and use our calculators here. This actually ends up being what? I think 9 times the square root of 3 if you're rationalizing, but we said we weren't going to do that. So 27 divided by the square root of 3. Oh, whoa, 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 that was weird. Hang on a second. I didn't want that. There you go, and hit enter. Okay, there we go, guys. 15.59 if we're going to round to the nearest hundredth. So we'll write that down. 15.59. And that's going to be our length for j. So that's our short leg. 15.59. Now what's missing, everybody, is we need our hypotenuse. And to get your hypotenuse, you're going to take your short leg, which we just found was 15.59, and very simply, we multiply that by 2 to get the length of the hypotenuse. Now, the best way to do this in your calculator, you guys, is not to manually type in 15.59, but for me, I've got this little ANS button right here underneath my 3. For those of you using a TI calculator, I believe your ANS, your last answer feature, is the second function of the negative button in most cases. But if you're just using your phone calculator, and actually I could have done this here, there's no reason to do anything. If I just hit the times button, oh, nope, this one didn't. But on most calculators, it'll just use the last answer that it had of 15.59. So I've got to go here, answer times 2, and that gets us a hypotenuse here of 31.18. If we're going to write that one down, 31.18, and that is going to be the length of the hypotenuse. And I suppose if I wanted to check this, let me do this one more time. It's probably, in fact, I know it's not going to work out perfectly, but let's try it, guys. 31.18 is my hypotenuse, squared, minus one of my legs, which I think was 27, right? Yeah, 27 was the leg that we were given. So minus 27 squared, and then minus the other leg, which I can see on my page here, of 15.59 squared. Now, I'm certain this is not going to give me 0 because 2 of those 3 numbers are rounded decimals, but I got 0.1443, pretty darn small, and in fact, it's close enough. Let's see if I can do this right. I think that the hypotenuse was actually, in exact form, 18 times the square root of 3. So that if that's the exact hypotenuse, squared, minus one of your legs, which was 27 squared, and then minus the other leg, which I'm pretty sure was 9 times the square root of 3. Get out of there, close it, and square it. That should equal exactly 0, and there again is a number in scientific notation with an exponent of negative 14. So this is 13 zeros, and then 8526. Close enough to 0 for our purposes right now, guys. So I feel pretty good about those 2 answers here. And everybody, that's a wrap on section 8.2. So you've got 2 things to make sure that you have memorized or at least written down carefully. And that's this diagram here with 45, 45, 90 triangles, where their pattern here is x, x, and x times the square root of 2 for the length of the 3 sides. And then this pattern here for a 30, 60, 90, where the side lengths are x, x root 3, and 2x. So we've got to have those down. Once we do, hopefully it's not going to be too bad to find the lengths of missing sides in these special right triangles.